right? Use linear approximation to approximate the square root of 81.3. Round to 4 decimal places. Okay, so the way this problem is set up, we can define a function f of x as the square root of x. So x could be any number. And one thing that we know is f of 81, because that's a perfect square, we know that's going to be 9. We want to find out, so what is f of 81.3, which is a value that's very close by, but how do we come up with that? It's not a perfect square. Well, the idea behind tangent line approximations is that over a small interval of a known value, there's not much change in the function. And so the tangent line can be used as an approximation within a small region. So, for instance, the square root of x. Its graph, we know, it looks something like this. And somewhere along the line here is x equals 9. And at x equals 9, there is a tangent line. All right, now, the square root is a very slow-growing function, which means around x equals 9, so around some range of values on the x-axis, there is a corresponding range on the y-axis that we can approximate with. So that's what we're going to work with, because the height of the tangent line is a good approximation to what the height of the curve is. So let's see how this might work out. First thing we're going to need to get is the equation of the tangent line. So what is the equation of the tangent line at x equals 81, so the known value? Okay, so to get the equation of a tangent line, we use y minus y1 equals m times x minus x1. We know the x and y values here, because the x value is 81, the y value there is 9. What we need is the slope at that particular point. The slope comes from the derivative. All right, so clearly we'll just look at this as x to the 1/2 power. So the derivative here would be 1/2 x to the negative 1/2 power, which is 1 over 2 square root of x. All right, now the slope that we're looking for is this derivative evaluated at 81. So 1 over 2 times the square root of 81, which is still a known value, and that is going to be 1 over 18. All right, because square root of 81 is 9, 9 of 2 is 18. So our tangent line, y minus 9 equals 1/18 of x minus 81. And we just need to simplify here. So y equals 1/18 of x minus, let's see here. Well, 9 would go into each of those, so I'll reduce. So 81 over 9 is 9, 18 over 9 is 2, and then I'm adding 9 to this side, so adding 9 is the same thing as adding 18 halves. So y equals 1/18 x plus 9 halves. All right, now let me take a look at a graph that shows this, the graph of the original function and its tangent line, so you can see what I'm talking about with the height approximations. Okay, this doesn't look too pretty just yet. I need to do some zooming to get a decent look at this thing, because remember, this is happening all the way out at x equals 81. All right, so there we're kind of getting close enough. All right, so at x equals 81, here's where my approximation is centered. And you know what, I'll close these. I just wanted you to see that this is the original function, is what we started with. And this tangent line works as we expect. So the tangent line is very close to the original curve around this particular point. So the idea is the height of the tangent line will tell us the approximate height of the function in a small region around the point that's known. So in order to figure out what f of 81 is, what we're going to do instead is let's call this function, let's just call it g, and that way g is the approximation function. So we're saying that f of 81.3, which is the square root of 81.3, is going to be approximated by g of 81.3. Now the thing about g of 81.3 is this is a linear function, and a linear function is pretty easy to plug into. So we would do 81.3 divided by 18 plus 9/2, and I'll just approximate that. So 81.3 divided by 18 plus 9/2 is 9.0167. And that should be our approximation to the value of the square root of 81.3. Now, we do have a calculator that can do that for us, so let's go ahead and check to see how close that was. It's pretty good to about the 5th decimal place. Well, to 4 decimals it's accurate, so that's a pretty decent approximation.